Hello everyone, and welcome to another CNCM lecture. I'm Noah Scheinbaum, and this topic is on finite differences and their applications in competitive math. So, for starters, what is a finite difference? So, it's fairly simple. A finite difference is any mathematical expression that can be written in the form f of x plus a minus f of x plus b. Sorry for this pop-up here. Thank you, Mac operating system. When a finite difference is divided by a minus b, that creates a difference quotient, which is the basis for the limit definition of a derivative. So here are the difference quotient and the limit definition of a derivative, comparing the two. We're not going to go deep into this because this is not a calculus class. This is analyzing the effect of and the uses of finite differences in competitive math. But interesting fact for those of you who have taken or are soon to take calculus, this is where this comes from. So what are the actual uses for this? Finite differences are often used to determine the degree of a polynomial, right? So let's say, for example, you have the polynomial f of x equals x squared minus 7x plus 17. But you don't know that you have this polynomial, right? You're just given what this polynomial is equal to at a bunch of different x values. So say you're given the x values 0, 1, 2, 3, 4, 5, 6, and f of x is given 17, 11, 7, 5, 5, 7, 11 for these respective x values. Well, you can take the difference between these values, right? And you're just going to see this first difference between these. This decreases by 6, so this is negative 6. This is negative 4. This is negative 2. This is 0. This is 2, and this is 4. So the first difference, this isn't constant yet. So you have to go again. And to get from here to here, you would add 2. To get from here to here, you would add 2. To get from here to here, you would add 2. To get from here to here, surprisingly, you would add 2. And to get from here to here, you would also add 2. So by the time you reach your second difference, it's completely constant. So you know that the degree is 2, and the function is quadratic. And this works for any polynomial, right? You're not going to have it work for a sine function or a tangent function because those don't have degrees. But for actual polynomials, whether it be a cubic function where the third difference is going to be constant, or a polynomial of degree 2019 or 2020, sorry, I'm still stuck in the previous decade, 2020, where the 2020th difference is going to be constant, although that might not be too much fun bashing out. However, finite differences do have a lot of use beyond finding just the degree, right? And we're going to go through two AIME problems today to better understand that. So here's an example problem that I found that I thought was really, really good illustrating this concept. It's from the 1992 AIME, and it's problem number 8. The problem is, for any sequence of real numbers A defined as such, define delta A to be the sequence A2 minus A1, A3 minus A2, A4 minus A3. So essentially, right, you're just going to take two consecutive terms and then subtract them. Notice delta A is the first difference sequence, whose nth term is A n plus 1 minus A n. Suppose that all of the terms of the sequence delta delta A are 1, and that A19 equals A92 equals 0, find A1. This fact here, that all of the terms of delta delta A equal 1, is very important, because tying back into the previous thing, once you have a difference that is constant, you know the degree. So this is the second difference, right? Because we've already defined that this delta is going to create a different sequence. So delta delta A is just the second difference sequence, which means that this is going to be a function of degree 2. Now you could bash out the quadratic. I chose not to. I chose to solve it this way. You can plug this back into the original sequence, right? So you're just going to take like this difference minus this difference minus this difference, and create new differences. Now this is ugly. I will be the first to admit that this is really, really ugly. So I would like to simplify it, and you get this, which is a whole lot nicer, but not nice enough for me to say out loud. So take a moment to look over this. Okay, cool. And again, well, I'm very sorry about the formatting here. It's a little bit weird on Google Slides. Sorry that it cuts through. So notice that all of these are going to equal 1 because, like it said, all of the terms of the sequence delta delta A, which is the second difference sequence, which we found here, are 1. So all of these are going to equal 1. If you add up all of these equations to all of these n minus 1 equations, right, you're going to get this right here, an plus 1 minus an equals n minus 1 plus a2 minus a1. That is a mouthful. Using this derived equation, you can add it from n equals 1 to n equals 18, which gives you 18 times the product a1 minus a2, and then that minus a1 equals 153. Now, to get this number, right, you could add it all out. Yes, I know my disk is almost full. To get this number, you could add it all out, but you could also acknowledge that this looks a lot like Pascal's triangle, and you can derive that this number is actually just going to be 18 choose 2, right? So, in order to set up a systems of equations to solve for a1, add from n equals 1 to n equals 91 as well. So that will give you 91 times a1 minus a2 minus a1 equals 4095. Now, please definitely do not add this one up. Like the other one, you could probably add up and then confirm your theory that it goes along with Pascal's triangle. But please, if you're taking the AIME and you have a problem like this, and it seems that you have to add it up in a way that involves combinatorics, please just use Pascal's triangle, do 91 choose 2. It will save you so much time. So if you multiply this first equation by 91 and the second equation by 18, you can eliminate the a2 terms, right? These will cancel out. And then that will determine that 73a1 is going to equal 59,787. You can try this out yourself. And dividing through, that will give you a1 equals 819. So we'd solved the problem. Okay. The following problem is from the 2015 AIME 1. It's problem number 10. Let f of x be a third-degree polynomial with real coefficients satisfying the absolute value of f of 1 equals the absolute value of f of 2 equals the absolute value of f of 3 equals the absolute value of f of 5 equals the absolute value of f of 6 equals the absolute value of f of 7 equals 12. Find the absolute value of f of 0. So a cubic function can only change direction twice, right? If you can draw a function that is cubic that changes direction 3 times, please send that to me because I think you might have just broken all of the laws of math. If that is mathematically correct, you will probably earn a prize somewhere. But as far as we know, and as far as every single law in mathematics thus far of the subject tells us, a cubic function can only change direction twice. Now, the only way for a cubic function to satisfy the above constraint is for the local maxima and minima to be maxima or minima, to be in the ranges of between 2 and 3 and 5 and 6. Otherwise, more bends would be necessary, or the function would inexplicably flatten out, which is not mathematically possible, right? You can't have bends at between 1 and 2 or between 6 and 7, right? Because then you're going to get flattening out between. Yes, you're going to get flattening out. And if it changes direction between 2 and 3 and 5 and 6, then it would change sign between 1 and 2, 3 and 5, and 6 and 7. And I have this helpful little diagram here that is expertly drawn by me on some coordinate plane. I do not remember the website. I'm sorry. It might be GeoGebra. This means, right, that f of 1 will equal f of 5, it will equal f of 6, and f of 2 will equal f of 3, will equal f of 7. Now, if f of 3 and f of 5, right, these are both, one of them is going to equal 12 and one of them is going to equal negative 12. Either way, by symmetry, f of 4 will have to equal 0. Let's assume, just for the sake of simplicity, that f of 1, f of 5, f of 6 equal 12, and f of 2, f of 3, f of 5 equal negative 12. So let's just take out the x values 1, 2, 3, 4, 5, 6, 7. and f of x would be 12, negative 12, negative 12, 0, 12, 12, negative 12, right? Because as defined above, this is what we're using here, this is what we're using here, and then by symmetry, as we found on the last slide, f of 4 has to equal 0, because these two are going to be of opposite signs, but of the same magnitude. So the first difference between this, you subtract 24 here, between these first two terms. Between these two terms, it's going to be no change, so that's 0. Here we'll add 12, here we'll add 12, here it won't change, and here you'll subtract 24. And then the second difference between this, here you'll add 24, here you'll add 12, here you'll add 0, here you'll subtract 12, here you'll subtract 24. So then in the third difference, it's constant at negative 12, which goes along with what we initially thought because it was a cubic function. It has a degree of 3, so the third difference should be constant. So far, we seem to be doing everything right. I haven't made any glaring mathematical errors yet. So now knowing that the third difference is negative 12, we can work backwards. So the third difference, right, it's going to stay constant at negative 12. The second difference, I'm putting what we had before, right? This is what was on the last slide, but now knowing that it's going to go negative 12 from here to here, 24 minus negative 12 is positive 36. Negative 24 minus 36 is negative 60. And then f of 1 minus negative 60 equals 12 minus negative 60 equals 72. So you can use finite differences for finding a number of different things, right? There are two problems that don't necessarily seem very similar, but when you go down to it, finite differences can make them both much more simple. And there are other ways of solving both of them, right? I mean, I think technically if you wanted to, you could potentially bash out the equation for this, but you're not allowed a graphing calculator on AIME, and you don't have that much time to do it by hand, so thank you, Keenan. So this is a very efficient way of doing it, considering the other ways limit you either by time or by resources. So if you are still sticking around for this lecture, I just want to thank you. I know this one was a bit on the shorter side. Yes, I know I have problem of the day duty, Keenan. Thank you. I know this lecture was a bit on the shorter side, so I appreciate you guys sticking around. And Keenan's so thoughtful. Well, anyway, have a great day, everyone.